Hello? Yeah, just a couple of things before the beginning of the talk. So first of all, if you're going to throw away this, or you don't want it as a souvenir or whatever, we have a box outside so you can put it and we can recycle it. And then for those of you who brought posters, if you want to keep them or something, you can take it from the panels. Okay, thank you.
Okay, thanks a lot. And our second speaker this morning is Cornelia Vizman from Timisoara, who will speak about coadjoint orbits relevant to ideal fluid dynamics.
Thank you. Thank you. I'm very happy to give this talk here to these nice people in this nice place. And this is joint work with my longtime collaborator, François Balmaz, from École Normale Supérieure de Paris. And I will, the title, he found the title, which is relevant to ideal fluid dynamics. I don't know how relevant they are, but this is our hope. And I found it a good title. So let me start. Can you hear me? Do I speak loud enough? Shall I speak louder? Okay, thank you. So the plan of my talk is to give first an introduction about the ideal fluid flow, and then the kind of singular vorticities that we are looking for. So these are point vortices, vortex filaments. These two are codimension 2, and the vortex loops and vortex sheets are of codimension 1 in the manifold where the fluid flow is happening. So for the introduction, we can consider in general a Riemannian manifold M, but then I will specialize to the plane and the space R3 in my concrete presentation on vorticities. So we all know the geodesic equation on the group of volume-preserving diffeomorphisms with this right invariant L2 metric is Euler equation of ideal fluid flow. So here U is the velocity, so it's divergence free. We are in the ideal fluid, and P is the pressure. And we can allow also non-compact manifolds, then we consider compactly supported diffeomorphism, or manifolds with the boundary, and then the flow is tangent to the boundary. I put here this picture. I tried to put as many pictures as I could in this talk of mine. So it's just to see how the geodesic, this is the right one. So how the geodesic on the Lie group can be seen as comes from a path in the Lie algebra.
Okay.
And yes, so this is the U, the velocity, and the C would be volume-preserving diffeomorphism. So the vorticity, this is the vorticity 2 form is the differential of the 1 form U flat. Remember, we have a Riemannian metric. And it satisfies Helmholtz equation, which just says that the vorticity is driven by the flow. So in 3D, it is a vector field, the curl, and in 2D, it is a function. We just divide the 2 form sigma by the volume form on the manifold. So the vorticity lives in the dual of the Lie algebra. So the smooth dual is 1 forms modulo exact 1 forms. But if the first cohomology group is of the manifold is 0, then this can be identified with d omega 1, which is the space of our vorticities. So this is the smooth dual or the regular dual. And because the vorticity is driven by the flow, it is confined to a coadjoint orbit. And this can be seen also when we write the Euler flow as a Lie Poisson equation on the dual of the Lie algebra of divergence-free vector fields. So this is the Lie Poisson bracket. We all know this, the symplectic leaves are the coadjoint orbits. I wrote there the KKS symplectic form on the coadjoint orbit. And then for the Hamiltonian that comes from the constructed with the Riemannian metric, we get this Lie Poisson equation. But we are, I took this picture from the paper of Isosimov and Kezin. They they have more papers actually on classifying coadjoint orbits for the area preserving diffeomorphism of manifolds, and they use these Rabe graphs. So this picture is for diffeomorphisms of the disk that preserve the boundary. So I plan to look at singular vorticities. So the only cases that one can make sense of are if you want the support to be on a submanifold, so you want, then there are only these codimension 2 or codimension 1 cases. The codimension 2 case is already well known, but I will shortly go through it also. And then this codimension 1 case is our work, the new part of my talk. So the way we are proving that we really get coadjoint orbits, these spaces of curves and spaces of submanifolds, so these infinite dimensional symplectic manifolds you will see soon, is with this general fact. So the momentum map for the inclusion of a coadjoint orbit into G star is a momentum map for the group action, but the other way around, if we have a Hamiltonian action with injective and equivariant momentum map, so it's an inclusion and the action is transitive, then the manifold is actually a coadjoint orbit. So this is the way we prove these are coadjoint orbits. So point vortices. Here the group is the group, the Hamiltonian group. No? It's the area preserving diffeomorphism group of the plane. And the Lie algebra is described by, and we take compactly supported. So every compactly supported Hamiltonian vector field comes from a unique compactly supported Hamiltonian function. So we identify G with C infinity C. The point vortices, so here we have n points in the plane. They live in the configuration space, so we take out this fat diagonal, delta n, and we endow it with, naturally with the area form, which I denoted here by omega. And this J, I will denote by J the momentum maps, is the momentum map that realizes the configuration space as a coadjoint orbit of the Hamiltonian group. So the momentum map is given by these delta distributions. Gamma I are the vorticities of the points. And here we have the Hamiltonian function. This is coming from regularizing the Hamiltonian that we have seen when I wrote the Poisson equations. And so here is the green function of the on the plane comes into play, and here with this bold G I denoted rotation by 90 degrees. So this is classical people. James Montaldi, he has also in different types of surfaces has studied this. He did a lot of work for these point vortices choreographies. Also codimension 2 is vortex filaments. So here we have the group of compactly supported volume preserving diffeomorphism of R3, and we have the space of closed curves, embedded curves into R3, and the Marsden-Weinstein symplectic form is the KKS form on this coadjoint orbit. What does it do? We take two tangent vectors at the space of curves. So these are vector fields along the curve, but they have to be normal because the tangent part doesn't change the shape of the curve. So these are normal vector fields along the curve, this UC and VC. And we insert them into the volume form. We get a one form which we integrate along the curve. And this can be generalized to codimension 2 submanifolds in higher dimensional manifolds too. And it's still symplectic form. So here, the way the space of curves is embedded into G star, or stays into G star, is by this, X alpha is a divergence-free vector field on R3, compactly supported. Because H1 of R3 is 0, it always has such a potential. Alpha is a one form which can be integrated over the curve. So this is a momentum map for the action of the group of volume preserving diffeomorphism on the space of curves. And this can be, together with Stefan Haller, we generalized it to higher dimensions. So if H2 of M is 0, then we get the codimension 2 Grassmannian as a coadjoint orbit in the group of volume preserving diffeomorphisms. But if it's not 0, then one has to pass to central extensions. On the Lie algebra level, these are the Lichnerovich central extensions, and Ismagilov, he showed how to construct the associated Lie group extension, and the Lie algebra of this universal Lie algebra central extension is G hat given by these potential forms in omega n minus 2, these alphas, modulo exact forms, and then we get a similar injective map, the momentum map from the codimension 2 Grassmannian into the dual. So again, by from the Hamiltonian for the fluid flow, we via this LIA, localized induction approximation, this regularization, one gets the Hamiltonian to be the length of the curve, and we have the symplectic form, the Marsden-Weinstein symplectic form. And the Hamiltonian equation is the binormal curvature flow, which is written there in red. So we flow along the curvature of the curve times the binormal vector of module 1. This equation can be written for the arc length parametrization. So if gamma is an arc length parametrization of the curve C, then this is just this nice equation that is shown to be, whose solutions are mapped to solutions of the cubic nonlinear Schrödinger equations via this Hashimoto transformation that uses the curvature and the torsion of this curve in the space, and which is an integrable equation. And together with Stefan Haller, we tried to find some integrability features of this of the equation in higher dimensions. So in higher dimensions, we wrote this Hamiltonian equation. The Hamiltonian is the total volume of the codimension 2 submanifold. And now instead of the curvature times binormal, it is the rotation by 90 degrees of the trace of the second fundamental form, which is the rotation of the mean curvature vector field. And Boris Kasin came with the name skew mean curvature flow. And together with Young, much later, they found some features of the Hashimoto transform in this case. And for four-dimensional manifolds, Shashikant, and then Kasin in general, they showed how it is via LIA how one gets this. There is a mistake, it's vortex filament, not the vortex sheet. So, and now Huang and Tataru, they prove local well-posedness for this equation. They have two very recent papers. Actually, that's why I wanted to tell you about this, because it's still work on it. So this was codimension 2, and now we are passing to codimension 1. In the plane, codimension 1 is a curve, and we view the points of the curves as point vortices. And instead of these gamma I that were the vorticities, now we have a vorticity distribution, which is one form along the curve. So beta, which we assume to be nowhere 0. And I wrote there how we can view such a pair of a curve and of a vorticity density as an element in the dual, in the singular dual. G, remember, it's the can be identified with the compactly supported functions on R2. And the coadjoint action is the natural one by a diffeomorphism phi on the plane. So what are the invariants of this action? So one cannot change the, maybe I go back here. So the phi of C will have the same surrounded area as C. And the push forward of beta by phi has the same integral over the curve. So this integral, this W, we call total vorticity. And so it is also preserved. And these are the only invariants. The coadjoint orbit is OAW. And we can see that each orbit contains a round circle with uniform distributed vorticity but yes, the radius and then dependent on A and W. This is not new. This is one special case of this coadjoint orbits of the Hamiltonian group, which were studied by Alan Weinstein for Lagrangian and Lee, a student of Eckehart and Yael, for isotropic. And together with Francois, we have a dual pair description of them. And so these are leaves of the space of weighted Lagrangians. They are leaves of isodrastic foliation on this space. But in this special case, from the pair C beta, we can recover the parametrization of the curve. So the an arbitrary point x on the curve is the f of t, where t, the parameter, is just the integral, so that from x0 to x of beta, so it's kind of the total vorticity that is along the curve between x0 and x. And but f can be defined only modulo rigid rotations of the curve, because we have to fix this x0. Yes, and now I realized that I didn't say that actually we work with oriented submanifolds, oriented curves, oriented submanifolds, because we always want to integrate over them, so we need the orientation. So having this parametrization, the coadjoint orbit is the space of parametrizations modulo rotations, and I say reparametrizations by S1 W. So these are and the enclosing fixed volume A. What is the symplectic form, the orbit symplectic form on this coadjoint orbit? It descends from the natural symplectic form on the space of embeddings, which is just taking two tangent vectors. The tangent vectors along an embedding are just vector fields along the curve, and we insert them into the area form and integrate over the curve. When we do the action by rotations is Hamiltonian, and the momentum map is just the area surrounded by the curve, and reduction at A yields the symplectic, the KKS form and the coadjoint orbit. So the KKS form is a reduced symplectic form from big omega, and what we can find in the we can decompose the tangent space as zero integral functions on C times exact one forms. Namely, we view, so if this is the curve, we decompose UF into its tangent and normal apart. So this is rho n. And here we don't take lambda t, but we take lambda times the velocity. And because we want the area to be preserved, so this rho is has zero integral. So this is the first component, and the second component is given by lambda. And in this decomposition, the KKS form has this canonical coordinates, but it is on C, not on a neighborhood of C. The pairing here is this non-degenerate pairing between zero integral functions and exact one forms. And we can try to do dynamics on this Hamiltonian, and on this Coadjoint orbit. So the Hamiltonian, we could, I just wrote it mimicking the point vortex Hamiltonian and taking an infinity of points. So I hope this will work as I wrote it here. This I wrote during this conference in one night. So we take out the diagonal on C cross C, and we integrate this green function with our vorticity distributions. It has a simpler form in the language of embeddings. So the main result, our main result, is about the prequantization condition, which is that the A times W, so the area times the total vorticity has to be an integer multiple of 2 pi. And we arrived this, first we were really constructing the pre-quantum bundle, but then we tried to write a character for the Coadjoint orbit. So I recall here what it is. A pre-quantum bundle over a Coadjoint orbit is a principal circle bundle, P, endowed with the principal connection, and the curvature has to be the symplectic form. And now if we have the Coadjoint orbit O sigma of an element sigma in G star, then sigma restricted to the isotropy Lie algebra is a Lie algebra homomorphism, and if we can integrate it to a group homomorphism, this is a character. And there is a theorem of constant that when pi1 of G is 0, so for simply connected Lie groups, the character exists if and only if the Coadjoint orbit is pre-quantizable, but when pi1 of G is not 0, then we have to add this, the condition that the action of G, the Coadjoint action, lifts to a connection preserving action on the principal bundle, on the pre-quantum bundle. This one can see, for instance, when pi1 of G is 0, and from the long exact sequence, and the period of the symplectic form and the period for the character, they are linked via this isomorphism that we get between pi2 of the orbit and pi1 of the isotropy group that we get from the long exact sequence. For infinite dimensions, there are these works of Karl Hermann Abe where so there is also pi2 of G plays a role. And this is the way we tried to construct the pre-quantum bundle. So it is clear that one would look at the space of embeddings because the Coadjoint orbit is the space of embeddings modulo a circle. And on the space of embeddings, we have this natural one form that is constructed from nu. I recall that nu is simply the one form on the plane with d nu equal omega. So we really have this omega bar is actually omega kks in my notation, and but the problem is that this one form theta is not a principal connection. It doesn't reproduce generators. The generator for the reparametrization action is f prime, and we get in general A. This is one problem, and the other problem is that this is a circle bundle for a circle of length W, and then if we want to scale, and so there is this a problem, and under the assumption that the product of A with W is in 2 pi times an integer, we can fix the problem. We just factorize by the subgroup of rotations by the W over K. And here I wanted, but how we view this principal bundle modulo when you factorize it by zk. Then we have this k to 1 projection, k to 1 covering from C to the circle, the true circle, and indeed. Then we can view the principal bundle as k-fold coverings from our curves to the circle. This is another other description of the principal bundle. This we won't have in higher dimensions. And so this is the pre-quantum bundle. We also tried to find the character. There is a geometric expression of the character. So this is a homomorphism from defined on the isotropy subgroup. So what we do, so we take x on the curve, and an arbitrary curve that comes from the infinity, from infinity to x. Now phi is a compactly supported area diffeomorphism on the plane, so it fixes the infinity, and phi of x will be on the curve again. So here, and the area that is enclosed by this in this triangle. We denote it by a phi of x, and we can see, so here is also important that the curve is oriented. So you can see that if phi x comes to x from the other side, so then what we get is this small a phi of x is the, so one adds this a to the area, so it's defined only, well-defined only modulo a. And when we integrate over C with beta, then it multiplies with the integral of beta over C, which is the total vorticity, and which is W. And so one can see again that AW must be in 2 pi Z in order to make sense for of the character. We have this algebraic formula we got when we looked, because we looked also in n-dimensional case. So this was the first approach. We make everything in the general case, but then we step down to 3-dimensional and then to 2-dimensional case. So we have this description of the character, which is interesting because it appears this the total vorticity between the point x0 and phi minus 1 of x0. Here q phi is the unique unique function, compactly supported function that satisfies phi star nu minus nu is the q phi, and so nu is this one form. And so this we can see here that it is this definition works also for phi that preserve only the curve, not the one for beta. And indeed, we can define the character can be extended to this subgroup H that the Hamiltonian diffeomorphism that preserve only the curve. This is the polarization subgroup. So this is all the work of these mathematical physicists, Goldin, Menikoff, and Sharp. So we can extend the character also to the polarization subgroup. They observed that these polarization subgroups exist for codimension 1 vorticities, and they do not exist for codimension 2 vorticities. Okay. So I prepared also 2 slides about my joint work with my PhD student Ioana. So we considered pointed vortex loops. So we combine the 2 cases we have, the weighted loops and the point vortices, and here, so we have these n points, x1, xk, k points, x1, xk in the configuration space of the curve. So they lie on the curve, they have vorticities, and the action is the natural action. So I showed there how it is the pairing with an element in the Lie algebra. The invariants are again the enclosed volume, the total vorticity, but also the vorticity, total vorticity between consecutive points, denoted here by W till WK, and of course the circulations of the points. But now the coadjoint orbit is the whole space of embeddings, so we don't have to factorize rotations, because let me go back to the picture. Here we needed to fix x0 in order to write the embedding, but now we can take as x0 the first point we have on the curve, and all the other points will be well placed because on the curve, because we have this condition that the Wi is the total vorticity between xi and xa plus 1. So really,
sorry,
yes.
Before I get lost, what are these circulations? Can you
Yes, so these circulations, the same, sorry, there is this, when we had the point vortices, so it was, let me go, just show you the, for point vortex dynamics, we had for point vortices, we had points, and we had these positive numbers, these vorticities gamma 1 to gamma n, and these embeddings with delta functions. And this we combine now with the vortex loops, where this momentum map is integral of the Hamiltonian function over the curve. And now we have the curve, and we have the points, and we add the integral of h on the curve. So, and we add this delta distributions applied to h, and we have these gamma i's. And they are fixed by the coadjoint orbit. by the coadjoint action, but all the others, C, beta, and xi are just pushed forward with the Hamiltonian diffeomorphism in the group. And now the identification, so if you have this embedding, then the image, the push forward of the canonical form dt, and then the points with parameters, this, how to say, these partial vorticities, W1 to WK, and then the gamma stays there. But what is so the coadjoint orbit is very simple. What is the symplectic form? It is the natural one we can write. So we integrate over the curve, and then we omega of the vector fields along the curve, and then we also evaluate them at the different at the k points we have on the curve. And it is an exact form, so here we have really pre-quantizability without any condition. Yes, you can write, using nu, one can write the one form potential for the KKS form. But here what is surprising, and I thank Yael for the question, so how it is, she was asking me, what is the, if we fix the curve and the vorticity, and we take one point, and we move it along the curve, what is the tangent vector that is paired in the KKS form with it gives non-zero, so what is kind of the canonically we look again at the decomposition of the tangent space, so as we had here, so into rho and lambda. So again, rho is zero integral because of the area, but now lambda, before lambda came into play only by its differential, but now lambda is controlling how the points move along the curve. So the second component, so lambda is really the function on C, on the curve, and so from this decomposition, if we insert them into KKS form, so then we see again canonical coordinates, but this time the non-degenerate pairing is the L2 pairing between the functions plus evaluation at different points. You can think about a single point, it's the same feature for, so it's a kind of, I don't know if this is the right English word, bluffing or something, it's surprising that you have this subspace which is in duality with the space itself. But this is because we have another pairing. So what we get are coadjoint orbits that have the same space but different KKS forms, because we add more and more terms to it. And we vary this W1 till WK. So maybe I should stop if there are some questions, because the next, I guess, I will pass to vortex sheets. No. Can I? Yes.
Hi, Cornelia. Is the purpose of, well, you say you have a dual pair on this embedding space, right? Is that right?
The dual pair, this works for, yes, in only 2 dimensions, because so we need the Hamiltonian group.
Okay.
So it's as in Marston-Weinstein's paper from '83. Yes.
And is the purpose of doing the pre-quantization so that the group actions you define are the momentum maps are equivariant, or not? Does it have anything to do with it? So, so let me rephrase it. What's the purpose of doing the pre-quantization of the coadjoint orbits?
Yes, so after pre-quantization, of course, now we would like to, quantization is difficult here because there is no, we are in infinite dimensions, there is no measure to integrate,
sure.
and so there is, yes, but you see, we have all this, we have the character, we have, so we can write the representation, we can, but it's, the Hilbert space is not here.
Okay.
Yes,
just
so this is,
okay.
we cannot go farther.
Okay, so it's just,
It's
I
just
thought it might be
mathematics.
related to defining an equivariant group action or something on the...
I don't know,
Okay.
maybe you can talk later.
Can I ask one more quick
Yes, please.
question? What was my, oh God, I'm blanking on what my next question was. I'll ask you later.
Okay, thank you. So then I will pass to vortex sheets. This is the codimension 1 vorticities in R3. So instead of a curve with one form beta, this time we will have a surface and a one form beta. So we will have, so we view the surface as a union of vortex filaments. As before, the curve was a union of vortex points. Now this one form beta assumed to be closed on the, and we take it nowhere zero, so that so the kernel of beta is a distribution. So this is these are the leaves, but we take all the precautions so that it is a vibration over a circle. So what we consider is a surface sigma and a one form beta, the vorticity density, which is nowhere zero and with discrete period group. The period group is WZ, so W is the smallest period of beta, and that's why, so it's, we can, if B is the log, how they call it, Cartan developing of beta, so beta is the logarithmic derivative of B, and this is the picture we have. So we view it as an element in the dual of the Lie algebra of divergence free vector fields, because now the group is, I will not write it, the group of compactly supported volume preserving diffeomorphism in R3. So what we do, we pair it with a divergence free vector field. So it has a potential alpha, which is a one form. So we just integrate alpha wedge beta over the surface. It's similar to what we had before. Then the alpha was a function h, and we just integrated h times beta over the curve. Just one more. I drew there a curve from one fiber to the other, from one filament to the other, because integrating beta over any such curve is the same as it doesn't depend on the curve we have chosen. It depends only on its projection. It's the distance from Z1 to Z2 on the circle. So and now I wanted also to reveal a bit of to open the door to the kitchen, and but I have to see how much time. 10 minutes. 10 minutes. Okay. So Here S is the model, but it will be a compact orienting surface of genus 1 because we want beta to be nowhere 0. So, and then we build first this Grassmannian, nonlinear Grassmannian of all oriented surfaces of type S. And then we will decorate it with one forms, beta. And then we will pass to the nonlinear Grassmannian of surfaces of type S, decorated with beta, and they enclosed on a fixed volume. So maybe I will, so the tangent space to the space of surfaces is given by, the tangent space at sigma is given by normal vector fields along sigma. But since we have codimension 1, we can use the metric and identify it with functions on sigma. So we will have again 0 integral functions on sigma because we want to preserve the enclosed area, enclosed volume. Again, with the ambient metric, we can decompose the tangent space. And this will be, ignore this beta sigma from C infinity, please. So it is just this decomposition in functions on sigma times exact one forms. And this will be, again, the canonical coordinates for the symplectic form. And if we pass to, how do we get the KKS form? So now we have this model one form on the model surface S, and we have the volume form on R3, and so mu and beta together cook up in the natural way one form on the space of embeddings. I called it the hat pairing, and I wrote a paper about how this works with these differential forms on spaces of embeddings or on nonlinear Grassmannians. So what we do, we have vector fields on R3. We insert them into the volume form, and we pull back to the surface. So this is a one form on the surface, which we wedge with the one form beta, and we integrate over the surface. And since, so this head pairing is, so this omega, it's actually built up from mu and beta. And it has functorial properties, so d omega is d mu dot beta plus mu dot d beta, and these are closed, and so we get a closed to form. But it is not, it has a kernel, and the kernel is exactly coming from the action of diffeomorphism that preserve beta, this diff plus S beta. So we factorize this action. This is a reparametrization action on embeddings, and the quotient space is the two form gives a symplectic form on the quotient space, and the quotient space. I skipped this. Where is this exactly? The line. So this. Principal bundle, maybe it works here. Diff plus S beta bundle embeddings over our coadjoint orbit. So we have this form mu dot beta here on the embeddings, and in descends to the KKS form here when factorizing the action. So this is the KKS form. In general, it is not exact, but the pullback to embeddings is exact. Oops, no, not even this. Oh yes, it is exact. Yes, because we are on R3, and mu is the differential. So this is the differential of mu dot beta, where mu is like this. So it has a canonical form for the pairing between zero infinity function and exact one forms. That's the same as for vortex loops. Yes, and this is the coadjoint orbit. So we ensure that the momentum map is injective and equivariant, and the action is transitive, and so we get the coadjoint orbit of vortex sheets. The vortex sheet dynamics, so Boris Casey proposed the Hamiltonian function that comes from the Hamiltonians for all these vortex filaments that compose the surface. So we take the length of all these fibers and we integrate over the base. So he wrote it for beta, an exact one form. If we write we compute the Hamiltonian vector field, I write it in the decomposition that comes from the Euclidean metric in R3. So the first, so this is the in C0 infinity sigma times d C infinity sigma. So this was the decomposition where the symplectic form had the canonical expression. So here the geodesic curvature, the normal curvature of the curve, and the geodesic normal vector field along the curve appear. So they are they are defined for each filament in the vortex sheet, but since they are nice coming from a vibration, we extend it to the whole surface. So this is the first expression, but we can view it also with KB. We decompose the binormal vector for each of the vortex filaments, and we take the tangent and the normal part. And then in the second part, so we insert it into beta, and then we take the differential of this function, and this is the second component. And I did not prepare now. I gave a talk online talk in Utrecht about this vortex sheet dynamics. If I have, no, I can tell you, you can ask me if you want to know more about this. We have some results. The pre-quantization condition is as before. The product is AW is in 2 pi z. We have again a polarization subgroup, those that preserve the surface and not the vorticity distribution. So this is, I have to mention this work of Goldin, Mennikov, and Sharp, because they work on, so we have closed surfaces. They have vortex tubes and vortex sheets, so they go from infinity to infinity, and all these vortex filaments go from infinity to infinity. And they arrived to a very similar formula, but they have done it while with the physical reasoning, and so it fits with our construction. And one can write the character also on geometric formula, but now we don't have the area. And with this I will end. For the curve, we were considering curves from infinity to a point on the surface, but now we have the surface, and we have at each point z. We take the fiber, and then we consider this dz with boundary, the fiber, and then we let it flow with the with an isotropy from identity to phi. So this will go to phi of CZ. If phi is in the isotropy group, then this will be again a phi, but if not, it's just a curve. And then we take the volume swept out by this isotropy, and we integrate it over over the base. So we take all the fibers, and there is also a similar algebraic formula for the character, which in the case of the isotropy group involves the flux homomorphism for the one form beta. And I think this is it. There are some references here, and yes, thank you for your attention.
Yeah, thank you, Cornelia. So do we have questions? Anton.
Thank you for a nice talk. So you were discussing those coadjoint orbits and KKS forms and pre-quantization, but do we know something about the H2, about the second chemology? So this is non-trivial, there are many, like, kind of course there were many cases, but in some, at least in some of those cases, do we know like the chemology group where those two forms take values, or how?
Which H2? Which
H2 of the orbit.
Of the orbit.
Yeah, but I mean,
okay.
omega, right?
Yeah.
The KKS forms take kind of, they define classes in H2, but what is this H2? Was it trivial to start with, or was it non-trivial, or how large it was? If I'm not mistaken, sometimes you were saying that's the same space, but there are several forms. Like,
yes.
From that perspective, would be interesting to know whether, of course, that's an infinite dimensional story. Maybe we don't have control of H2, but maybe sometimes we know something.
Yes, we didn't thought about this, but for the case of vortex loops, this would be very interesting to see, because there we don't we need this pre-quantization condition. Yes, and yes, thank you. Thank you for your idea.
Other questions?
Hi, thank you. So in this combined case in which you combine both point vortices and circles, like how do you combine to have a Hamiltonian formulation? This maybe I missed it, but.
So we didn't look at the dynamics yet. This is what I hope you and I will do. Yes. So by now we have the structure for the geometry of the orbit, and then now the Hamiltonian. I hope to combine the two Hamiltonians that I wrote for point vortices and vortex loops.
And then another question is, so this like, let's say, approximations of the Euler equation, do you really get it by taking, like, let's say, smooth Euler with compactly supported and taking limits, or is it not so?
The case is the codimension two cases. They are solved with this localized induction approximation and so. And in the codimension one, so this is something we would like to prove.
So you can't really formalize this as a limit?
Yes, I do hope, yes.
Okay, thank you.
Thank you.
Other questions? Yvette. Mic is coming.
I was surprised that there was so little functional analysis on infinite dimensional spaces in your talk. Did you suppress these
Yes.
these considerations?
Yes, I did.
But they are there.
Yes, there is this. Yes, I wanted to show the pictures and.
Thank you.
Thank you. Yes, you are in infinite dimensions, and there are all these problems. And I want to mention also that we were doing also for a general manifold M, and then the cohomology of the manifold will play a role, but then one can generalize these things, but they became a bit more complicated.
Yeah, that actually would have been my question about, so the ambient space you can take was
Yeah,
basically manifold.
yes. So for the diffeomorphism group, then one has to pass to the central extension, and the universal one, that is the Ismagillov's extension, and yes. And then we also plan to do with the case when for the surface, but when beta has singularities, and then I do hope that these pictures. Actually, that's why I was showing this picture from Boris Kezin's paper. So I hope that we can describe them somehow. Rape graphs, I don't know.
All right, if there are no further questions, let's thank Cornelia again.
Thank you.
And let's take a 5-minute break.